Okay, welcome back. So now we've got Jacob Lister, and he will be giving us his talk, Write Your Own Modular Synthesizer in Golang. Thanks.
Hello. All right, I'm Jacob. Just a little bit about me. I live in Wellington in New Zealand. I'm married with no children, but one cat. Cat isn't actually all that interested in synthesizers, especially those low bass notes. She just runs and hides under the bed. I've done a broad variety of things. I've been in so many industries in the software development, I'm losing track of them now. I started in embedded systems development and firmware development for RTUs and SCADA engineering and that sort of thing. I've done a fair amount in 2D graphics and drawing and editing tools and that sort of stuff. And I've been in the internet service provider industry with telecommunications and network engineering for quite a bit of time as well. And a little bit of agri-tech in there too. And now I work for a payroll company, which is where the sinkhole of Java developers end up. So this talk is just going to be a wrap up of a few things. I'm going to talk a little bit about building your own synthesizer, why I'm picking Golang as an implementation language, some of the challenges that go around creating a user interface for that. I'm going to talk towards the end of the talk a little bit more about the software design and just how I actually build this thing for a multi-platform. But on testing and benchmarking, and given we've got a little bit of time, we might just take a little bit of a look under the hood about how the code's put together as well. When I'm not doing my day job stuff in my home time, I'm very interested in music technology and building and writing music software. So very many years ago, I wrote a little application here called the Carbon Looper. This is a fairly conventional MIDI sequencer and sampler. So a screenshot of that here, you've got these red blocks which are me playing my guitar, and these green ones which are the sampling software playing it back, and that just basically sort of builds up a song like that. So as you can see from that screenshot, that software is written in C and C++. The user interface is GTK2, and it's getting rather long in the tooth, so I wanted to basically do a refresh. For that refresh, I had a few new aims, looking at a technology stack that I could actually pick. And one of the things that I wanted to get out of this was something that could be very sort of social. So I wanted an application where I could just actually run it in JavaScript in the browser and share it on the web without needing any installation. And I just, as it's a home project, it's unconstrained by time and deadlines and that sort of thing, so I can just work on it when I have time and slowly build it up. So my long-term ambition for what I'm trying to do for this is something like a piece of software called Reactor or other comparable products like Max MSP, where you can basically have this modular arrangement, lay out your individual processing units graphically, and then connect them all up and build your own synthesizer. So why Golang? I looked at quite a few potential implementation languages for this, and the reason I settled on Golang in the end is that it's got a lot of compile targets. So I've actually got multiple ways that I can build this application. I can build it to a native target using native audio hardware with very good real-time performance. Golang also has an excellent JavaScript transpiler, which will actually just produce JavaScript output that you can actually then just run in the browser. There's also a lot of activity in the space of a WebAssembly target, which looks like the future for running code in the browser as well. On top of that, there's even transpilers for C and C++ that are quite experimental. So there's a lot of options, which is basically why I liked it. How do you start building a synthesizer? Actually, I really like Darren's talk, and one thing that I've decided in presentations is that if your diagrams are too complicated to draw in ASCII art, then there's probably too much going on for a presentation. So I thoroughly support the effort to make your diagrams and ASCII art. The other thing is that, at least in a Go presenter, you put these dots down the side of the page. It sort of lines things up, and it also makes it look like it's come out of a dot matrix printer from the 80s. So, a little bit about what's going on here, this block diagram. This is basically the minimum processing units that you need in a synthesizer to make something which is going to start being musical. So the main thing is what is an oscillator, which is just a periodic waveform generator, which will produce a tone. An envelope generator below that, which basically shapes the noise. So when you hit a key, it usually rises to its maximum volume quite quickly and then sinks off. And then a gain, which basically just multiplies those two inputs together. So on the left here, we've got some control signals, which are inputs to that. And the main ones are the frequency or the pitch that you want, and a trigger, which is just basically an impulse that says things need to start now. So with all that sort of decided in Golang as a implementation language, a product to build being a minimum viable synthesizer, and some requirements, which is the multi-platform stuff. So I want to be able to run this at least on Linux and Windows, and also in the browser. And I want to be able to build a user interface where which I can run for all of those compile targets. So that really presents quite a bit of a challenge because there's a lot of activity in the Go space on user interface at the moment, but no real sort of clear standards. So I decided to add another one. So some of the alternatives I looked into when deciding on a user interface was perhaps on some platforms I just don't have one at all and just run it headless for the native code. Perhaps I build up sort of a minimal client-server sort of REST API, but that looked like it was going to be a lot of work. And perhaps I actually port low-level graphics, STM or HTML Canvas, which I may actually look at doing eventually. But for now, here's my idea, which is stream the DOM. So basically what I've done is I've built a client-server application where most of the audio processing is running on the server, but the user interface runs in a browser and it's connected by a WebSocket, and I stream DOM updates back and forth. After doing quite a bit of work with React, the front-end JavaScript library in the last couple of years, I've decided that's quite a natural way of working, and it's quite easy to implement something similar. So after talking about it for a while, let's have a look at it. So that's rather large, at 100%. Right, so here's the building blocks of the application that we saw in that minimum viable synth document. So on that left here, we've got a MIDI input, which is basically taking MIDI events from an external device like a keyboard or so forth, and translating them into control signals. Oscillator generating the tone, envelope generator shaping the noise, and gain producing the output. I've got a little keyboard here, and so if I press the keys, we can hear the notes, and a few scopes in the middle. I think if I try my luck and arpeggiator, that should be fun. There we go. And that scope down the bottom is showing first one being the tone, and that second one being the output of the envelope generator. So, just a little bit more about what's going on there in terms of the user interface. We turn on some logging. Yeah, we can see as I move those around, we can see those. Yeah, scroll back. It's a lot of events. Just find one. You can see those patches coming back, and basically that's just a list of instructions of what are elements in the DOM to update. So that'll be just a colour change. You can see as those signals are going through, the colours on the connectors are changing, and so there's basically just some update and feedback going on there, showing what's going on. And just to make that just a little bit clearer, if I were to just produce a second window there, which has a second connection, you can see there's another client there, and now those are following along. So that's a nice, simple way to get a user interface out of a platform that's not really built for web development right now. Just to have a little bit of a look at the code and what that looks like, you have something that looks similar to how you'd build things in React and JavaScript. You're just building up a sort of development and then having various tags underneath it and registering event handlers for callbacks and so forth. So some limitations of that approach. It's very much one event and then one updated user interface response coming back. So anything that you'd sort of normally do client-side for front end, event propagation, event bubbling and that sort of thing is not possible. So you have to be a little bit creative about how you manage your user interface event handling. No browser-side API calls. I can't sort of go out to the internet and start making other calls or anything like that. And could potentially be quite slow over a WebSocket. So up till now, we've been talking about the native build, but it can build for JavaScript as well. So if we simply go to that URL, right, we can see exactly the same application, all running in the browser, and it's not, the audio's not coming out because it's coming up my laptop, but it does work. All right, so just a few more things about how this is put together. I really encourage everyone to read this book. It's a very good summary, Clean Architecture by Uncle Bob Martin. It's a very good summary of best practice design patterns in the industry and how to structure an application well. And while this is actually more talking about conventional, kind of accountancy applications, there's a whole chapter in there on embedded systems and about how some of those design principles can be sort of ported in. So in the audio clean architecture, we have this concept of basically sort of onion architecture or concentric circles. You can't really draw circles in ASCII text art, so we're using squares instead. But the idea here is that we have kind of an inner sanctum or an inner layer of audio component processing, which has no knowledge or even awareness of the existence of the layers outside it. And so as we move further out, we get into user interface, and then further out again, we actually hit the hardware. So the sort of golden rule is the core of the processing logic shouldn't know anything about the platform. And they're just those basic inputs and outputs again. Audio and MIDI go in here, and storage here, and UI here. It's probably not the most, testing and benchmarking. We'll come back to a few things actually. What I would like to show you is just some of the progress that I've been making over the holiday break and some new patches. So what I intend with this sort of as a presentation platform is to just build up a suite of kind of introduction to digital signal processing and synthesis 101 with a number of worked examples that you can easily just kind of work through and manipulate. So we've looked at the minimum viable synth. We'll just look at some other synthesis methods now. This is an example of additive synthesis. So if we just press these keys now, right, what we'll see going on there is we have a construction of a more complex waveform through additive synthesis of the harmonic series. At the top we have a fundamental note. Below that times 1, below that again times 2, and then below that times 3. So as you start adding those waveforms up in the harmonic series, you'll start artificially constructing more complex waveforms. And you can sort of see that as that's pressed, we get that approaching triangular sized wave. Another principle there is if we take just the odd harmonics, we'll see that that wave starts taking on a more square appearance, and it starts thinning out and sounding a bit more hollow as well. Moving into some modulation techniques. This one's a bit of a behemoth because it does both amplitude and frequency modulation at the same time. Here we've got the concept of what we call a low frequency oscillator, which is a periodic waveform which is operating in ranges normally below the audible, but can be used as a control to modulate the wave. So in this configuration it's set for frequency modulation, so if we hit that key, we can see that that wave on the right is then sort of swaying in and out in a kind of vibrato effect. If I switch a few switches there, one there, isn't it? And that will off. That's RFM. Right, a little bit more subtle, but now I've got no, that's less subtle. Now I've got amplitude modulation where we're actually varying the amplitude of the wave rather than the frequency. So you can see all of that basic stuff can actually be built up quite visually, and it's quite easy to demonstrate it. So just have a little bit of a look at the code. When I add these processing units, one of the things that is going to be quite important is because there's just going to be such a volume of them, you'll literally have hundreds of different little modules that do one very specific thing. It's quite important that they can be added in a very simple way. So if we look at like the most simple example, this is just a sum. The code is literally just a couple of lines that needs to do that one thing. Part of the reason that Go is quite good for having a lot of compile targets is that the bulk of the compiler tool set is actually in the standard tools. So it's very easy to parse Go and Go, and it's very easy to generate new Go code in Go. So what I've got going on there is basically a little builder generator which will parse that file and then generate a more thorough output like this, which adds these methods like start and stop if you didn't add them, creates a definition saying what parameters it has and so forth. And then when we come to the user interface and we want to add a new one, we just drop it in and all the user interface is built. So for the simple case of actually just adding a new tool, that can be actually done quite easily. And then you can't remove it, but we'll just... Testing and development. Yeah, this has been one of the more challenging parts of building a tool like this is that because it's building for multiple compile targets, and particularly JavaScript, it's good to have a handle on how well the code is performing on a just pure sort of benchmarking approach. So Go has very good tools for that. Here I've got a set of benchmark tests which I can basically run the same test for both the Go implementation and the transpiled JavaScript and just see how they compare. This is quite neat. You just set up a little snippet and put it in the test harness, and the test suite itself will just exercise it until it's got enough data and run it a million times and give you an output summary of how long it took. And when I run it, I can hear my laptop actually whirring up as that exercises the metal. Right, we can see the result of that output there. Like certain things, like just making a single function call, you actually get like almost identical overhead between the native target and the transpiled JavaScript. And then some other things, you'll see this compile interpreted engine single sample. So one of the other challenges with this, actually I should also those patches we were just looking at. There we go. That's what one of those patches looks like saved out. So it's just XML. It's really simple. We've just got a list of the processes that are there and a list of the connectors and where they go to. So the format's really simple. The next challenge that you have to actually run this thing is you need some kind of a strategy to actually walk through the graph and then process each sample at each point. So the way of doing that is basically a topological sort of the graph, which will give you a list of the order you need to traverse the modules so that the dependencies are all met and the previous data from the previous operations are in sync. The ideal way to do this is actually do it on every sample, and at 44,000 samples a second, that's a lot of calls. So the overhead of making a function call is actually more than doing the work. So when we start having benchmarks like this, it's quite helpful because it'll tell me things like this. Single sample example here is saying the JavaScript version is actually 40 times slower than the compiled one. So that's something I'm just, the reason for that is it's abstracted over basically a polymorphic interface in the Go call, so that's quite slow. So it's just not something I can do in JavaScript at the moment. All right, well, I think we might just take some questions if people would like to know anything more about.